So today we want to get back into the topic of inverse functions. And inverse functions, as we talked about on Monday, are nothing more than a way of reversing the role of input versus output. Right? The same relationship between two quantities, but what used to be the input of one of those functions, one of those relationships, becomes the output instead, and vice versa. So they just trade places. So just thinking from a data table example, let's suppose that we just do, let's just look at this table right here for a function that's called g. Right? So g of 0 is equal to 3, g of 1 is equal to 1, and so on. So if I thought about this g as though it were a machine, then as an example, if I put into that machine an input value of 3, what do I get for the output? What's g of 3? 2, exactly, according to my table. So let's suppose I take that same data point, this one right there, 3, 2. And if I wanted to make a statement about the inverse function of g, if it exists, right, then how would I say, what would be an example, what would I call the function which, when I give it the input of 2, produces the value 3? So how do I write the reverse relationship here? When I plug in a 2 into the inverse function, I need to get a 3 as the output. What do I call that inverse? How do we use notation to write inverse function here? G to the power minus 1, right. So these two statements are exactly the same. They convey the same information as one another, right? When the output of g is, when the input to g is 3, the output is 2, which means that when the input to the inverse of g is 2, the output is 3, right? So the input and the output have just traded places. So if that is the case, I can ask a question like, for example, what is g inverse of 0? How would you answer that question? Exactly. So I think that's probably the best way to do it, is to sort of put a question mark there. G inverse of 0 is something, and whatever that something is, trade places with that something and the 0, right? And what we're really asking then is how to turn something into 0 via the function, not g inverse anymore, but g, right? G inverse of 0 is whatever, if and only if g of that whatever is equal to 0. And so how do I answer the question, g of what is equal to 0, using this table? How do I know it's 4? Yeah, exactly. In the x row, the input that gives the output of 0 is 4. Right? This data point right here is what's answering that latter question. But that latter question is exactly the same as the original question, g inverse of 0. So we'd say that g inverse of 0 is what? That would be 4. Right? So that's one way of looking at g inverse. If I'm asking you for g inverse of something or f inverse of something, what I'm asking you for is an output of the inverse function. But that's the same as an input of the original function. So you might think of g inverse of 0 as asking me for an x value from my original function instead of a y value from my original function. Right? And we can take that same idea and think about it in terms of formula and also think about it in terms of graph. So suppose that I have the graph of some function. So let's say, first of all, let's say that I have a graph of a function that looks like this. This is y equals h of x. And I'm just going to label some points on here. So maybe this is the point 5, 3. Maybe this is 4, 1. Maybe this is 2, -2. Maybe this, we'll pretend this goes through the origin. And then maybe I'll put another point over here, -1, 1. All right, so here's some points on this graph. Suppose that I wanted to know what is h inverse of 3. How would I find it, or where would I find it? At the point 5, 3, how do I know Well, so first of all, how do we answer the question then? H inverse of 3 would be equal to what? 5. Because trade places. H of 5 is equal to 3, exactly. So trade places, and when we trade places between input and output, the function H inverse becomes the function H. H of 5 is equal to 3. And again, we know that's the case because that's what it means to have the point 5, 3 on the graph of the function H. Right? So the fact that this point is on the graph of H, 5, 3, means that H of 5 equals 3, which means that H inverse of 3 is equal to 5. Okay, now, what happens if we do H inverse of 1? We could get 2 answers. What answers could we get? -1. Or we could have 4. Question mark, question mark. So how do we resolve this problem? Which one of these two is it? So the only way to resolve this is to say that H inverse of 1, in fact, because it can't have 2 values, it can't have any value at all, right? So why? Because H inverse needs to be a function, right? The inverse function is called a function because we want it to be a function. And so since a function can't have 2 outputs for the same input, right? H inverse of 1 is, we're just going to say that it doesn't exist, right? How could I know, so what feature of the graph is telling me that H inverse of 1 doesn't exist? What's the relationship between the 2 points on the graph that you use to get these numbers? Where are they? The y value has, they're right, the y value is equal to 1. So I'm going to be really kind of sloppy here. Draw a horizontal line. This horizontal line goes through the 2 points that both have the same y value, namely y equals 1. Right? Y equals 1. And so because these same the same y value corresponds to 2 different x values, we can't have H inverse of 1. And so what do we say? We say that this graph fails the horizontal line test. Exactly. There's a horizontal line that meets this graph in 2 or more places. So the graph fails the horizontal line test. So H inverse of 1 doesn't exist. In fact, better still, what we will say is that H inverse does not exist as a function. So this actually was, Max, your question in our last class, like, does this inverse function thing always work? The answer is generally no, right? A lot of functions have graphs that don't pass the horizontal line test. What tests do all function graphs pass? What does every function's graph necessarily pass? Yes, not the horizontal line test, because that's the one. So this graph fails the horizontal line test. But what test does it pass? The vertical line test. So the vertical line test tells me whether or not a function is even a function, whether the graph is even the graph of a function, right? So vertical line test, all functions. In fact, that is the graphical tell of whether any graph can be the graph of a function. Every function graph passes the vertical line test, but only invertible functions pass the horizontal line test. Invertible functions only. Right? So keeping those 2 things straight as you think about how graphs are used to communicate about functions is important.